So for those who just joined the class, so I uploaded the makeup exam with the maximum score 60. It was a 70, and I also uploaded the homework number 2, and you have about a week to do. I think it is doable within a week. All right, and good luck. All right, so today we're going to talk about routing. So what is routing? Okay. What is the sound component? Routing. So what is routing? Construct the directions from starting point to the destination. So from A to B, point A to point B. How can you get there? So this is map of the Korea, and from SUNY Korea to COEX. How do you get there? Which turn should I make? Then how does navigation knows that well? Okay, that is basic computer science. And the routing, same thing happened to us. Same thing happened to the routing. So I want to deliver my message from SUNY Korea to the COEX, some computer networks. How can it be connected? And how can that packet traverse? Okay, so it is basically two concepts, and forwarding and routing. We learn about the forwarding. If I have messages, I deliver to the switch level to the forwarding. So routing is a little smarter than a switching level. L2 is a switching, routing is a L3, layer 3. So forwarding table is a data plane and directing a data packet to an outgoing link. Something is coming up, so I let that packet knows which path, which link you should take as a next hop. Okay, individual router using forwarding table. And routing is a control plane. So computing path the packets will follow. So whole packet. So after this, you have to follow that line. Okay. If you ask someone else on the street and how I get to the SUNY Korea from Triple Street, okay, go to there, make a left turn, right turn, and go straight, and you can find on the right. Okay, the whole plan. So routers talking amongst themselves, so they know what is the global look like, global view look like, global view of the packet, global view of the street. So individual router creating a forwarding table. Then whenever new coming in, and they let the which direction, meaning which router you should go to next. Okay, so this is the icon of the routing, and usually using something is coming and something is going out. So why does routing matter? Why is this important? Because routing decides the performance of end-to-end performance. End-to-end performance meaning because your communication and your packets are decided by the in the middle guys. In the middle guys, not that many. Like if I want to connect it to the COEX from SUNY Korea router, then Yeonsu router, Incheon router, then Seoul router, and Gangnam router, and that COEX. Okay, not that many. And quality path affects the user performance. If I'm taking a crowded router, then it will be delayed. But if my router is smarter, then I can detour with a faster. Even I take in more router hops. Okay. So propagation delay, throughput, and packet loss. These are metrics which determines the router determines which path should I follow, or which routers should I direct him to. Okay, use of network resources, and router using a network resources balance to traffic over the routers and link, meaning if there is someone is so popular than the others, then it'll be a bottleneck. Okay, if there is something which is less popular, meaning their packets will be faster. Okay, because router knows the neighbor situations. So whenever new packets coming in, just reroute to them. Then they can balance itself. Okay, avoiding congestion by directing traffic to lightly load links. So if the packets coming, so many packets are coming to the popular router, then I have a multiple choices. Which router should go next? Okay, rather than go to the first one, the higher priority, then I can go to the second and third randomly. Then I can load balance. I can do the load balancing. Okay, and transient disruption of the during changes, and the failure can happen. And maintenance meaning something is unpowered, power down and coming back. and how can you handle those? And how can you handle the load balancing properly? So limiting packet loss and delay during the changes, then the router which about to go down should let them know, should let the neighbors know. Okay, therefore your neighbors can predict it. Okay, when the new packet is coming in, rather than give it to the about to sleep guy, then I can detour. Also, something goes failure, then I can, if the neighbor knows that, how they know? Sending it, but there is no response for a certain amount of time, then I can estimate that router is a failure. Then I let also my neighbors, then they also notice by the this traffic. So I have to quickly find, and if I know it is done, if it goes down, then I should have ability to comes back. So when it comes back, it notice neighbors, then your neighbors know, oh, you're welcome back. Okay, then they can reroute it and do the continue to load balance. All right. So different types of routing. So routing in GPS devices, we are using a faster time or a shorter distance, or I prefer to go to the offload, or I prefer to go the cheaper road. Maybe I can prefer to go the better view. Okay, something like that. Okay, writing in GPS devices, maybe 3 or 4. Okay, which one is cheaper? Which one is faster? Okay, which one is the shorter in just terms of the distance? Okay, and the same thing happened in computer networks. Routing in the view of the shortest path or smallest delay and highest reliability and avoided congestion node. Okay, this differentiate depends on the packet itself. If I need a no delay communication, meaning like a voice or a live, I'm taking a smallest delay. If I'm sending a huge file size, then I want to deliver the highest reliability. Why? If it goes down, I have to resend it again, and I want to avoid the congestion node. Okay, and shortest path being I just do whatever I can do best. Okay. So routing can be represented as a graph. So routing is a graph problem. So network is mapped into the graph and graph vertex and edges, and where each link has associated cost, meaning from vertex A, vertex E, the cost is 1. Vertex A to vertex F is cost of 6. Okay, so cost is delay or financial cost or probability of failure or something else. So we can simplify, and we can make we can transform the real world problem to a mathematical problem by converting to the graph. Okay, then if it comes to the graph, then everything gets simpler and I can solve it mathematically. Then there is an algorithm, we call that algorithm, and the DVR, distance vector algorithm, distance vector routing is a DVR. So distance vector algorithm and construct a one-dimensional array of the distance to all other nodes. So from A, what's the cost B? From A, what's the cost E? From A, what's the cost F? Okay, what's the cost of C? What's the cost of A to D? What's the cost of A to Z? Okay, then it can be represented in an array. Right. Source to destination A, B, C, D, E, F, G. Then destination A, B, C, and G. Right. How do I get to A to A is itself? A to B is 1. A to C is 1 hop. A to D is 2 hops via C. E is 1 hop. F is 1 hop. G is either 2 hops, 4 hops, then I should choose a 2 hops via F. I think we can fill it in all rest of it, right? From source to destination. So DVA is construct a one-dimensional array of the distance to all other nodes. So one-dimensional node, distance to from me to all others. Then this one is maintained as a routing table of A. Okay, and exchange information with the immediate neighbors. So B has the same thing, similar thing, right? The C has a similar thing. Then if I can exchange, meaning A can have a global view, then they can figure out which way is the faster. Then they can calculate it. And update distance based on the received information and stop sending updates as soon as no change occurred. And example, so unit cost for each link if it is one and hop information kind of things. Okay. So distance factor in the global view from A, so source to destination. A to A is 0, A to B is 1, C, E, F. If you go to back, B, C, E, F. Remember this. So B, C, E, F was one hop. And if I cannot reach there initially, then I can set to infinite. Same thing happened. Let's say take a look at the G. G in the view of G, D, F. In the view of G, D and F is only connected. Then D and F is only connected. So A maintains this one dimension, and G maintains this one dimension. So if A collect the routing table from B, C, E, F, meaning A can B, C, and E, F. If this is the what A can see, 5 of them, they can connect it better, which means they can update the D and G is faster. How? Let's look at it. D. So among those who can reach D, okay, C can reach it. Okay, then I can reach C by one hop, then D can update it too. And let's look at the G. Who has a connection to G? Okay, F has. Okay, by hopping to F, I can go to G with the 2 hops. Do you see what I do? Okay, maybe too straightforward. Okay, then the local view, okay, in the view of the A, in the view of table of the B, C, D, E, F, G. Okay, so A has connection A, B, E, F, and G has a connection in D and F, right? So this is the initial local view. Then what do? Then among its adjacent, then they are exchanged. Therefore, they can update. Oh, I can go to G and I can go to D with the by using C and F. Okay, exactly what we've done. And some of the with the one hop communication, maybe some of the still is not reachable. Okay, still not reachable. Then what can we do? So my routing table, my local routing table is updated. Then I exchange updated one. Then by doing this, I can connect in everybody by 3 hops. Okay, if this wasn't solved, then I may still have the infinite. And if I keep exchanging, then maybe I can find the faster way. Okay. So come back to the point. So what if it happens? The failure of the between F and G. What can you do? So then F and G is instantly know there is a failure. Then F and G is a table of the F, table of G, right? So F cannot connect to D and G. Let's look at F cannot connect to G, okay, because G's connection was disconnected, and D also. F wants to be whenever F try to connect it, they were connected by a G, so they lose the 2 connection. And G connected to very many, right? G was connected by a D and F. Whoever connected by an F, I lose the connection, which means update to infinite. So I lost the connection to F instantly, and this information, A and E was connected by an F, then the connection, the link cost is updated to infinite. Okay, link connect, update to infinite. Then the routing table knows, oh, something bad happened. So something failure happened. Okay, then this propagate. Then the A to G is also be impacted. Okay, because 1 hop and 2 hops and 3 hops, the propagate and the cost is updated to infinite. And when it's 3, so when it is a failure, it comes back. What happened? I have to detour, right? So if I see the failure, okay. So A was connected to G and D and by a F. So F, so look at the table of the F. F was connecting to G and D and they are connected. Then what should I do? I should go reroute through this path. Reroute this path. Okay, and reroute this path. Okay, then I could be reconnected D and G. Let's look at the table G, table F. So I can connect to F and G, the D to G, and the F to G. D, E, F, look at, okay, so here it is. D and G is lost, and D is now connected by with the 4 hops, and G is connected by 4 hops via A. Okay, so I have to reroute. Okay. So count infinity problem. So what's the count infinity problem? So let me pause in here. Let's chat about it. So do you understand how I done it? The DSR, DVR distance vector. No question about it? Too easy?
I think it's good for now.
Okay, then. I think it's easy to understand it. Okay. Okay, let me continue. So if we have a hops, okay, is the epidemic concept, extending and extending. So what happens? It is keep extending. Then messages are overflooded. Then we call the infinity problem. Count infinity means, okay, my message from here, let's say this failure happened to here, then goes this way and goes this way and goes this way and goes this way, and goes this way. These receiving multiple times, and after receiving D, these are delivering to this way. If a message from C, if the message comes from E, then go to this way. The messages are keep looping through. Then the same messages are repeating and repeating. So we call this count infinity problem. A advertises a distance to infinity to E. Okay, connection 2 is lost, and I can scream in and updates its neighbor. Then C updates. C advertises the distance of 2 to E. Oh, E was something bad happened. Then keep advertising. And B also keep advertising. And A updates its table and advertising of the 4 via B in the reroute. And C updates its table by advertising by 5 via A, meaning it's keep increasing. So the message comes from this way, okay, then goes this way, and come in this way, including this, and it comes back to here. How about blue one? Then message goes this way and this way. This can be ignored, and this way again, looping through. There's also another path. Message goes this way, go this way, and go this way, and go this way. So same messages are looping through 3 loops. Then my value is keep updating. Oh, something bad happened, +1. Something bad, oh, is it reroute? I thought I have a reroute, but it turns out it advertising new information. Then I have to update, then I have to update. Then the count infinity. Okay, my looping through and my numbers to that point is keep increasing. So how to solve this? So let's talk about how do we solve this. So you understand the problem, right? So our approach is basically epidemic approach. Something bad happened, keep notice your neighbors. If it comes back, okay, epidemic again. So what happens? The message making loop, and it keep increasing is a value. Okay, so infinite, infinite, infinite. How can you solve this? So when the B is receiving multiple messages of the same thing, how can they block? How can they not forwarding it? That's the problem. Okay, how to solve this? Let's think about for 1 minute, and I'm going to ask you to how to solve this. So let me call. Okay, so I'm gonna ask 다정, 호진, 승재, and 예은. Okay, how to solve this? Okay, think about for 1 minute, then we can discuss together. 호진? 호진 and 승재? Not there. 호진 not here. 승재 is here. 승재? 호진 not here.
Not pretty sure about it. Sorry.
예은? Ready? Is she here? Yeah. You ready? So you guys understand what we are doing, right? Then what's the solution should be? How to solve this problem? Anyone?
Professor, can I go?
Sure.
I think we can limit the number of hops.
Oh, perfect. Okay.
And then if it exceeds the number of hops, we make the packet to resend.
Okay. All right, perfect. So what Hamin's idea is, so if the packet's hop is more than limit, then I can discard it. Okay, this went through so many times. This hops so many times. Okay, that's the TTL concept, time to live concept, and it's perfect. Thank you. And Yeon, I cannot hear you. Maybe you can speak up now, if you want to. Yeon, no, I cannot hear you. I'm sorry. Okay, who else? There's multiple solutions thing for this problem.
May I go?
Sure. Yanshik, let's give it to Yanshik.
I think that if there's loop goes on, it's like A to B, B to C, and when the message come back to A, then it shows that there's loop, which is not reached to the E. So maybe it sent to failure and stop the loop. Is it possible?
So you mean that if the message is delivered previous by my me, then
Yeah.
you're discarding it.
Right.
Okay. Okay. Yeah, that's how we do it. And I think, thank you, Yanshik. Great solution. Who else?
Can I go?
Sure.
Like, can we use like a flag system? So if one node receives the information about the disconnected E, then it marks itself as a flag turns up, and then to notify that the others that I have already received that information. So the following node that the neighboring node tries to send that flag node would know that received the information, so I wouldn't send it to that node, but instead the other way.
So basically, same approaches. So it's coming from, except it is coming from me or it's passed through me. I can keep sending it. That's the approaches, right?
Yeah, I guess.
Okay.
Yeah.
All right. Great. Thank you, David. Okay. So almost all solutions are already coming out. Okay. So let's see how people solve this. So solution A, use a maximum hop count to instead of infinity. Okay, maximum hop. If it comes to the multiple hops, then I can discard it. Okay, that's what the Seungjae was talking about, right? And solution B is split horizon. Then because the router is the fixed location, it's not moving, then I know the geographic location, an XY point of it. So do not send updates on the neighbor that provides info for particular right. B does not send the update to E to A since E learned from E from A. Meaning, if it is the packets are coming from me, then I don't do. Like the David and Yanshik says, right? Okay. And split horizon with the poison reverse. Poison reverse is B advertise at the route cost of infinity to E, ensure that A does not use B to E, get to E. So if it is looping through, then oh, you are not, you shouldn't. So the poison reverse meaning, so if that comes from the message I sent it and comes back to me, then that is a poison reverse. Then I can ignore that. The solution do not always work for the loops when there is more than 3 nodes. If the configuration is very tough, configuration is very complex, then sometimes it is not working properly. Okay. So how do you solve it in reality? What happened if it happens to reality in real system, then how do you solve this? So let's talk about this. So this is the conceptual. But if the node is so many, so popular, so dense, this doesn't work. Why? So count infinity, if you think about the count infinity, I have to care about the 16 routes or 17 routes. To cover 16 and 17 routes, I may have to update more than 30 to 40 hops, which is not feasible. Okay, because of that messages, the routing tables are contaminated. Then split horizon, whoever comes back to me, okay, then maybe update my reroute. And this can be also contaminated. So dropping it maybe is good. Sometimes it is a good idea, but dropping it sometimes give me a poor information. Okay, so poison reverse are the same approaches. Then in reality, how do they solve this? So does anyone know? So in reality, routing table does not moving because they don't have a wheel. And also its routing path is very rarely updated. Okay, so meaning that the routing path is not actually impacted. Why? Because so let's say I have the SKT update the new hardware, and SUNY Korea updates the new hardware. So SUNY Korea job is giving to the SKT. Then from the SKT, they can handle it. The SKT keep updating their devices every 2 years. SUNY Korea, maybe 10 to 20 years. Okay, so SUNY Korea's a nice job is delivering to the smart guys, So routing table itself, I'm just learning from the smart guy. I don't update. that periodically. But I'm just learning from them. So, and the routing path is basically based on the policy. Policy meaning, so how can I handle the message coming from that point, that point? So I write the policy, okay, just sending everything to the SKT. Meaning I'm dumb, but the SKT keep update the router and device is much faster. Oh, then my routing table will give it much simpler, and SKT will handle it because they will periodically update the hardware. They are maintaining whole global view, and they hire much expensive guys. Okay, so that's basically what we do. So if I set up the SUNY Korea's router, I don't set up the, okay, how to do this DSR. No, I don't do that. But I'm sending, whatever comes from inside, meaning from the SUNY Korea, just deliver to the SKT. I don't do loop prevention. I don't do nothing, but I do the secure, and I set the firewall. Then I'm sending everything, if it is okay, to SKT. And if the message from SKT, I'm accepting it. Okay, so very simple in real world. So routing. So the next protocol is routing information protocol, RIP. So previously, the network is the vertex. The edge was a link. Distance vector algorithm where vertices are network, not the host. Okay. So vertex itself is a host, not host itself. The vertex where vertices are the networks. The networks itself is a vertex. So valid hop count, this is 1 to 15, and 16 representing infinity. A limited fairly small networks is something like previously. I set the node as a host of the host as a vertex, host as a vertex. Now I'm setting the vertex as a networks. So networks are connected by networks, and these actual links are again is the cost of the networks. So link is the cost, and vertex itself is the cost too. So now the hops are infinity is a 16. If it is smaller than 16, it keep working. So this concept is much simpler, but it only works. It's a fairly small network. When the network grows, this complexity cannot handle. Okay, so there is and this routing information protocol is not commonly used, but this one, link state information, is very common solution. So link state is basically path selection method. So destination based. So from this guy, how can I connect to everybody? Then how can I connect to everybody? Meaning the destination based. So I want to reach this guy. Then if you know that guy, just keep forwarding. Okay, so destination based and flood information regarding immediate neighbors to all nodes. Okay, everybody let me know I want to connect it by this guy. Then each node obtain the complete map of network. So hey, I have a map of this guy, so I'm keep advertising my existence. Then they know this guy's existence. Then update how many hops then can reach there. Then they are each node keep advertising. Okay, then everybody can have the global view. So shortest path problem. So this happened to the shortest path problem because everybody knows everybody's cost. So given network topology with link cost is hop information. So cost of the link is cost from node X and to Y, point A to B. Infinity if X and Y are not direct neighbors initially, and compute the least cost path to all nodes. So this one is initial, and you are keep computing. The cost is hops, also the link cost. Link cost is specified in here. Link cost could be delay, link cost could be of time or distance. So from a given source to source U to all other nodes, U, then cost, and let's say this is U and this is V. And this guy in the middle has a cost, already has a path to V, right? Then predecessor node along path the sources V. So if you want to be connected to V and connected by advertising this information, then this information keep advertised and advertised. Now all the nodes are discovered. All the nodes in the network receive the message from you. So in the middle, guys, advertise, so path to the B. Oh, I know that guy. Then this reverse path will be selected. So this called the flooding messages. Flooding messages are delivering. Unicast is I'm talking to the one guy. Multicast is I'm talking to multiple guy. Broadcasting is I'm talking to everyone. Okay. Flooding means I'm doing everybody in flooded manner. So waters are flooded, right? So if I 1-to-1 is unicast. So I forgot to bring my iPad. I'm sorry. So multicast is multiple guy. Cast. Broadcast, whoever is connected will receive its messages. Okay. This is broadcast. And flooding is broadcast as concept, but it's keep doing this. Rather than just not once, then network will be over flooded. The message will be flooded. Okay, that is flooding concept. So if you remember if you know the Dijkstra algorithm, Dijkstra, the shortest path algorithm, do you know the Dijkstra is learned in the 213 and 373 and many basic computer things, right? So Dijkstra algorithm, if you don't know, don't worry, I'll review it. So Dijkstra algorithm is an iterative algorithm. After k iteration, and each node knows the least cost path to k nodes. So k iteration and multiple iterations, then you can know the destination to everybody. So if the k is enough, okay. S is a node whose least cost path definitely known initially. Set number of the S where it's a source node and add one node to S in each iteration. So dV is a current cost to the path to the source to V. Source is mine and destination is V. So initially, so distance of the V is cost of the U and V. U is my source. For all nodes, V is adjacent to U. Then it is, if it is adjacent, I can know initially. But if it is not adjacent, then I can set to infinite. So continuously update distance factor as the shortest path are learned. So I'm going to show you what is the algorithm, the basic algorithm initialize. You are initially set path to E itself. Okay, so in the current S, I have nobody but me. For all nodes V is adjacent to U, then this is one hop information, else is initially to infinite. Then looping through while W not in the S with the smallest distance weight, then keep W to S, then U is extended, right? So S is extended with the S and new member, then update the distance to adjacent to W and not in S, then minimum cost with the U and the neighbors and 1 hops and 2 hops, 3 hops with the distance value. It will be keep increasing with the smallest value. So I have animation, so don't worry if you're not clear about it. So U is me. So now my S is only me. So with the 1 hops, this guy is now my member with the cost of 2 or 3. So S is 3, right? Then I'm with the new cost, let's write down in here. So S, U, let's say A, B, it was B, right? C, D, E, F. So now with the 1 hop, S become U, what was it, C? C and A. With the distance factor, is U itself is 0, to C is 2, A is 3. Okay. One more, then this guy, S become U, C, A, D, B. U is 0, 2, 3. D is via 3, via C. V is 6 via C. Do you see what I do? Okay. Then S is now S is now this way. Then you can keep updating. So in the end, all the members are in S, and this information will be updated. Then, meaning, if from U I want to get to who, then I can know the minimum cost and via whom. Okay. All right. Clear. So Dijkstra algorithm knows from me to everybody and the cost. Okay, me to everybody cost. This guy is 3. This guy is 5. This guy is 6. This guy is 3. This guy is 2. This guy is 6. This guy is 8. Okay. So if the path 3, 2, 1 is updating, then this table should update to 7. Okay, something like this. It's periodically. It's like organically moving. Okay, something new values are changing to 1. Then I should update to 4. Then via this guy. Okay, this is good case. What happened is bad case? Clear. Eraser. Pink. 6 was 8. What if there was a bad case? Is let's say this link is updated to 20. Then this link increased to 23. Oh, you know what? I have 6 paths. Then I should go to 9. I should reroute to this guy. Okay, so how can you do this? Dijkstra can do this. Why? So every node advertising. Okay, how can I get to you, everybody? Then everybody, whoever receives it, and reversely delivers information. Hey, you know what? It was reachable by a 3. You know what? It was reachable by a 5th. And the cost is reversely delivered. This is basic Dijkstra algorithm. So even bad happen or something good happen, we can like organically update its value. Okay. Also, then knows to information to everybody. So to this guy, how can I get to this guy? How can I get to? So from this U value. So in the end, it's confirmed and confirmed and confirmed. Then every node is confirmed with the multiple hops. Then in the end, I can set up U, V, X, Y, W, S, T, G with the full path, meaning shortest path from U to everybody. Then forwarding table to V. So if I want to connect to the V, how can I connect it? Direct connection, UV. If I want to deliver to W, direct connection, UV, which is cost 3 and cost 2. X, how can I get to X? You know what? Via this path, you are reachable with 3. UW, by using this path, your cost will be 3. Then in the W maintains also this kind of thing, and forwarding these messages, U to X, then they are delivering. Then let's Y. Y is UV connection with the cost of 5, right? In the V of the U. G I want to connect it to G with the view of the U, then the connection will be this guy, U and V. And cost will be 6. S is in the view of the U, then UW, cost of 6. T, in the view of UW, and cost of 8. Okay. So this is what maintained by the maintained forwarding table at the view of the U. So this is basic Dijkstra algorithm. How does it look like? So we know what to. So first step was the initial guy, and the one more step is 1 hop, then 2 hops, 3 hops, and keep information. Keep updating this information. From source, the member of S is keep expanding it. So we've done this, right? It is more systemically wrote, and with the multiple iterations, even the value is not clearly, even the value is not updated, they are doing this steps because there is path to discover. So when all the nodes in the network is discovered, then they can stop. Okay. So I assume you understand this table. Very easy, right? Initially, what we do. So S2, in the view of the S, V, and W, only 2 are connected. Let's go back to the point. UV kind of thing. Okay, here it is. So in the view of U, V and W is only connected. V and W only connected. And with the cost and the initial neighbors is U with the one with the adjacent, then you are keep increasing. Then if it is fully discovered and there's 1 hop and I can eliminate those, then you can keep expanding it until you discover everybody. Okay. So back to the link state information. Each router keeps track of the state of incident link and link status working or not working, or cost is delay or throughput. And each router floods the link state in the entire network of my messages. It's keep epidemic concept. So every router gets a complete view of the network, and each router runs Dijkstra algorithm to obtain the shortest path to all other destinations. And link state information is advanced to OSPF, open shortest path first, and link ISIS is intermediate system and intermediate system. So every router actually doesn't broadcast every messages. Think about the all over the world. We may have millions of routers. If I have to communicate, it's not concept. It's this concept that's not working, right? Because I don't want to update the Stony Brook's the routers. I don't need to do that. Then what do? Then we do the system itself. Okay, IS. Okay, in this Korea, there's hierarchical concept. Korea that has multiple smaller. Then from there, it's smaller. So if I am in the tier 4, I only care about the tier 3s or tier 4. If I am tier 3, and I only care about the tier 3, among tier 3 under the tier 2. Okay, in the tier 2, I only care about tier 2 under the same tier 1. Then tier 1 does the tier 1 among the tier 1. So it's tier concept is system we call intermediate system and intermediate system. So determining the shortest path, shortest state of the link. So how can we update the link status information? Link status information properly. So periodically exchange hello messages to enable. That hello message is used as, oh, I'm survived. I'm still alive, right? Hello, keeps ending hello. So detect the failure at the threshold number of unanswered hellos. So I said hello, but he didn't answer, meaning he's dead. Okay. So distributing link state information is flood the entire networks. Or every node floods a link state packet on all links but the incoming one. So if the message wants to deliver to X to someone else's, then X to its neighbor adjacent list. Then A and C is delivering same message to B, and B is the messaging to D. But if you think for the human brain, it is straightforward. But in the concept of routing table, so whoever comes to me, okay. So if the A is messages, this path and this path, two paths, right? Then D deliver. Then what if A is coming in? What about this path? Let's change the color. What about this path? So it should travel like this. Right. So how can you ignore? So in this case, 1, 2, 3, 4, 5, 6, 7 messages, 7 deliver. So how can you make 1, 2, 3, 4, 5 messages from 7 to 5? How can I limit the 7 to 5? So B is receiving 2 messages from A to C, but it turns out the messages are originated from X. Then B must open the packet and checks the all path. So if there is overlap, then I can ignore one of them. Okay, then I can deliver to D only. Okay, by doing this, we can prevent the flooding, the more flooding. So if we don't do, we only checked what is coming from me, then I will keep forwarding to C if the message is from A, because I'm only check where it's come from. Then it's loop through, right? So if I have ability to open the packet of the all paths, then I should open it properly. Then I should block it. Okay. So flooding, distributing link state information is basically flooding concept, but even you are using flooding concept, you should have ability to open all the paths it went through. Then I can make decision, do I say it to you again or no? Okay, then I can eventually prevent the overflooding messages. Okay, so link state packets are the packets to be distributed in this way. A has B and E as association node and cost. And let's look at this guy F. F has adjacent to B, E, D, B, D, E, and the cost itself. So this is initial link state packet information, and sequence numbers are prevent the node from using old messages. If there is a sequence message and age. Sequence message, this message sequence, and if it is coming from me, then I'm increment 1 value and increment 1 value. So I just received the sequence number 34. Let's say C just received the sequence number 34 for the messages. Then if the message is coming sequence number 30, meaning 30 is the old messages, then I can discard. Then I can only update the latest information. This is not payload information, but this is about the link status information. Hey, link status information. Hey, am I alive? Am I alive? How's your routing table sequences? Then that message has a sequence number. If the message is coming 24, hey, 24 is old information. I don't need to. So I have update one. Take a look, receive this. Okay, that is a function of the sequence number. Age is time to leave for the packet. So if it runs through too many times, why do I need this? If it runs through too many times, meaning there's high probability that it is looping through multiple times and receive it again. Then I can kill it. So it's doing doing very similar jobs, but two mechanisms to kill the old messages or loop messages. Okay. So when to initiate flooding? Flooding is the worst thing, but sometimes we have to do. Okay, flooding. When should I do the flooding? Flooding is let everybody knows, like a screaming. When should I do that? When topology change, meaning this node goes down and there's new router comes in, or okay, I'm changing room of the router. So if I unplug the SUNY and SUNY router everything goes to IDC. Okay, I should let them know. Okay, so link link or node failure or link or node recovery. So it goes down and goes up. Something kind of this big happened, then I should do the flooding. I should scream to everybody. And configuration change, link cost changes, meaning if my network is from Cat5 to the fiber optics, I should let them know. It's good news. I have the screaming, okay? Or bad news, or we had a budget cut, then I cannot update. And that they took all our fiber optics. Then I should come back to Cat5. I should tell them, okay? And periodically, and refresh the link state information. Typically 30 minutes, every 30 minutes, routers exchange the link state information and corrects for possible corruption of the data. So if there's something bad happen, they should doing periodically. So, based on periodic. So it is not known by the message itself, but while doing a periodic message change, they can notice that. So link state versus the distance factor. We talked about distance factor and link state, right? So link state, so distance factor we talked about in the first part, and the second part we talked about link state. Link state tell every node in the network about your immediate neighbors. Distance factor tell only to your neighbors about every node in the network. So two concepts different. So OSPF protocol is selected protocol. It is commonly used among the routers in today's technology. This is the packet look like. So version information 1 to 4, but if the version flag is 1, it is hello message. Oh, we know what is a hello message. It's survival. I'm hello, hello, hello. I'm keep asking. If someone is not replying to my hello message, meaning he's dead, right? Request and send messages. And so request this information. Oh, there's a reply. Okay, and there's a send messages. Oh, I received the well, that is ACK messages. And area ID is where node is connected to in case of hierarchical routing. So area ID is if you're using a hierarchy or tier concept, then it is flagged. And authentication types. So authentication type is here. I can use a 0 authentication, meaning just flooding, just deliver information. And 1 is a simple password, and the message should be encrypted. Or if message 2 is MAC level encryption, or 3 or 4, or WEP in SCP, and many kind of the encryption and encoding. Okay, so LSA, link state advertising. What does this advertising messages look like? Okay, this is message look like cost of link, network connected, and TTL, time to live, and hierarchy info, and all this information is given and defined in this packet information, packet format. If you're not following, then the message cannot be delivered properly. So link metrics, it could be hop count or delay or something else as a combination of it. So we usually use a combination of it. So link metric is a hop, assign metric 1 at every hops. So hops, hops, hops. So list hop is a list cost router, or it is delay. Delay is you have to have a timer. Wait assigned to each link. Average delay for packet passing through is a delay, and problem with the simply using delay is instability. A heavy loaded link would oscillate between busy and idle links. Busy and idle links. If it is only using a delay. Because when the heavy packet coming, then delay become longer, right? Then if the smaller packet coming and delay packet, it gets smaller. Then if you're using only delay, okay, that path took longer because there is a heavy traffic there, and it will oscillate between two. So wide value range is a link could look hundreds of times more expensive than others, may cause a very long route. Because if something goes on, then that path looked like so big, then I should go reroute. But it's actually not, but it's time variable. So we shouldn't use just delay, but we should use the delay plus the hop count or the throughput and many combination of those. Then we should find the proper combination. Then we can choose it. So in the real world, for the most of the part metrics are static, meaning the metric doesn't change over time that dramatically. So there is no dynamic adjustment, but hard-coded by the network administrator. So we learn for an hour, okay, there's this method and this method and this method. In real world, and we don't actually using it, but we are just hard coded by the administrator. Something like if the message is coming from Sunny Korea, oh, deliver everything in SKT, okay? And something, this kind of thing is the real world. Then we call the policy-based routing. And we will talk about the next slide, next class. And this avoids the route oscillation problem because route oscillation is happening because it's dynamically changing it. You know what? My traffic is estimatable, so I don't do the dynamic. Okay. That's the real world approach. So most commonly used metric is W. W is a combination C divided by B. So C is a constant and B is a link state information. If there is an alpha value, which is a C, so we just keep dividing with the bandwidth. Okay. So let's talk about the hierarchy. So hierarchical routing, this is a more common concept and it is scalable for very large network. Previously, we talked about every node as one node, every node as one node. But if we have hierarchy, then reason one, among their tiers, they communicate. So there's leader and leader to talk to leader, okay? There's a leader to talk to leader, leader to talk to leader, and leader to talk to leader. So other nodes doesn't need to care. So in the view of this one, how many nodes do I have? 1, 2, 3, 4, 5. 5 nodes. Rather than 1, 2, 3, 4, 5, 6, 7, 5, 3, 2. So it's a, rather than looking as a 14, then I'm only looking 5. Why? They are tiered. Hierarchy. Then it is a scalable. Without hierarchy, it is not scalable. I cannot have ability to maintain 1 million. But I have ability to maintain 16 router properly, right? Then from there, then it's your subordinate problem. Okay. So cluster routers into areas of regions and scalable solution for very large network. And full table of A look like this way, okay? 1A to 5E. But hierarchy table for 1A look in this way. So 2, 3, 4, 5. If I want to go to the reason 2, I can go to B connection. I can go to B connection. I want to connect to C. By doing C, I can connect to reason 3. If I want to talk to reason 4, I can connect to by this C. If I want to connect by reason 5, I can connect by this C. Hops in the view of the leaders. Okay, rather than I maintain the huge and long tables, I can maintain hierarchy, which is much simpler and much straightforward. And it is a scalable. Scalable meaning I can keep expanding it. But if I have to maintain full table for everybody in the router, I cannot do that. So hierarchy routing is reduction in table size comes at the cost. The router between particular node pair may not necessarily be the shortest. So for the large network, how many levels do we have to do for the hierarchy? 1, 2, maybe. So let's say I have a 720 nodes with the hierarchy. If I'm using only one level, so I have to maintain 720 routers. If I have 2 levels concept, then I can make 24 regions, and per each region I can set to 50. So 29 local and 23 regional. So I only need to maintain 52. This 29 is local, my subordinate in this concept. 1B is 1A, 1B is 1C, and regional 1 is 2, 1, 5, 1, 4. Then with the 720 nodes, I can maintain 52 nodes. By maintaining only 52, I can make my my routing table is fresh enough. So if you compare 1 and 2, 720 to 52, wow, that is impact. That impacts, right? Also, if I have 3 levels, I can make 8 clusters and 9 regions per cluster and 10 routers per region. Then in the view of the local, my local is 10, so except me is 9. My region is 9, so except me is 8. My cluster is 8, except me is 7. So I only need to maintain 24 entries tightly. Then as I have more levels, then it is more efficient and hierarchical. So based on your topological distribution, then you can set your routing hierarchy in the multiple levels, then it is much more efficient to do that. Okay. Any question about today's class? No? Any question? No? So how about that question to the makeup exam? Nothing? No comment to the homework? No? Any comment? No?
Professor, I have a question for the assignment.
Sure.
I read the PDF